Hi, my name is Alyssa, and today I will be presenting on annotation and evaluation for audio. Before diving in, I wanted to give a brief breakdown on my talking points. So, firstly, I will start with background and basic application, then getting into evaluating the annotation and some challenges, and finally finishing with a demo that illustrates how a pipeline could work in real-world application. So, first off, what is annotation for audio in AI? Audio annotation in AI refers to the process of labeling sounds in audio recordings so that machine learning models can understand and interpret them. This can involve marking speech, music, background noise, speaker identity, or even emotions. These annotations serve as a quote unquote ground truth that AI systems learn from during training. It's almost as if you were to give an AI a labeled map of what it's hearing so it can recognize patterns and in the future make predictions. The main goal of audio annotation is to provide high-quality labeled datasets for training AI models. These labeled examples help AI systems recognize and differentiate between different audio inputs, such as spoken words, accents, or environmental sounds. This is especially important in applications like voice assistants, for example, Siri or Alexa, speech-to-text software, emotion detection, and even in security or surveillance where audio cues are vital. Without properly annotated data, these models would struggle to understand or respond accurately to real-world audio. The audio annotation process is a multi-step workflow designed to ensure accuracy, consistency, and usefulness of the labeled data for AI training. Let's break it down into four key phases. First, we collect audio recordings that are relevant to the AI's intended use. This could include voice commands for virtual assistants, ambient noises for smart home devices, or even musical clips for genre recognition. Before annotation begins, the audio is cleaned and standardized. This may involve removing background static, normalizing volume levels, and converting file formats to ensure consistency. High quality noise controlled input ensures better model training for later. Secondly, trained annotators or AI assisted tools listen to audio segments to identify specific events. Sorry, such as spoken words, emotional cues, or sound types like clapping or door slams. Annotators assign meaningful tags or labels to each sound. This could be like dog barking, female speaker, or angry tone, depending on the ultimate goal. Annotation tools often display audio waveforms visually to help annotators navigate the timeline. Precise start and end times are recorded for each labeled sound, enabling models to learn not just what happened, but exactly when it occurred. In many cases, additional context is added, such as identifying which speaker is talking, whether there's background noise, or noting overlapping speech. This enriches the dataset for more nuanced learning. Third, to maintain consistency and accuracy, annotations are reviewed by other experts or validated using automated quality checking tools. Discrepancies are flagged and then resolved. Annotation guidelines often evolve over time. Based on model performance or new requirements, teams refine how sounds should be tagged to improve results in the future rounds of annotation. And finally, once annotation is complete, the data is converted into machine-readable formats like JSON or XML. These formats include metadata such as labels, timestamps, and audio source IDs. Finally, the annotated audio is merged with the rest of the training dataset. The AI model now uses this structured information to learn patterns and improve its audio recognition capabilities. Now moving on into some of the types of annotation. When we talk about audio annotation in AI, it's important to understand that it isn't just one type of task. There are multiple forms of annotation, each tailored to specific use cases and technologies. The first and most common type is speech-to-text transcription. This involves converting spoken language into written text. It's essential for speech recognition systems used in virtual assistants like Siri, Alexa, or Google Assistant. It also powers subtitling services for video and supports voice-to-text features and accessibility tools. Accurate transcription helps AI systems understand what is being said, and it becomes especially critical in noisy environments or when dealing with diverse accents. Next, sound event detection. This focuses on identifying and tagging specific nonverbal sounds in an audio stream, such as dog barking, a door closing, or a car horn. This form of annotation is crucial for smart home systems, environmental monitoring, a smart security system, and so on. For example, a smart security system might need to detect the sound of breaking glass or shouting to trigger an alert. Annotators label each sound along with its timestamp and category to help the model learn how to detect these events in real-world scenarios. Moving on, emotion recognition annotations label audio segments based on the emotional tone expressed by the speaker. This type of labeling plays a huge role in humanizing AI systems. In customer service, for instance, detecting frustration in a caller's voice can trigger escalation to a live agent. In mental health applications, recognizing changes in emotional tone can assist with early intervention. Annotators use vocal cues like pitch, speed, and tone to make these judgments. Another important type is language identification. This involves detecting which language is being spoken in an audio clip. This is particularly valuable in multilingual environments where systems need to route speech to the appropriate language model. Whether it's for global call centers, automated translators, or multilingual assistants, this type of annotation ensures that AI can correctly process and respond to audio in multiple languages. And lastly, natural language utterance annotation focuses on classifying the intent behind what somebody actually is saying. This goes beyond the literal words and digs into what user means. For example, if someone says, "Can you turn off the lights?" the AI system needs to interpret this not just as a command, not just as a question, but also as a command. This type of annotation is foundational for building conversational agents and chatbots. Annotators label phrases based on intent, for example, command, question, request, and sometimes tag entities like objects or topics to help the AI understand the full context. Evaluating annotation in AI is also a crucial step that ensures models we build are both accurate and reliable. The primary purpose of this evaluation is to verify the quality of the labeled data that it's used to train AI systems, especially those designed to understand and process sound. In audio annotation, even small labeling errors like misattributing a speaker, mislabeling a sound, or even missing an emotional cue can lead to substantial performance issues in the model. Evaluation helps identify these inconsistencies early. It often involves comparing annotations across multiple annotators to assess inter-annotator agreement using metrics such as precision, recall, and F1 score to determine how well annotations align with established ground truth data. In some cases, automated validation tools are also employed to flag timestamp mismatches or inconsistent tagging. Moving on into different evaluation methods. Evaluating the quality of audio annotation is essential to ensure that the data feeding our AI models is accurate, consistent, and aligned with the task at hand. I want to go into 3 specific methods of evaluation: inter-annotator agreement, also known as IAA, ground truth comparison, and visual inspection with auditory review. First off, IAA is a statistical measure used to determine how consistently different annotators label the same audio data. In other words, it evaluates how much consensus exists among human annotators working independently on the same task. High agreement typically signals that the annotation task is well defined and that the annotators have a shared understanding of the guidelines. Common metrics for IAA include Cohen's kappa for 2 annotators and Fleece's kappa when there are more than 2. These metrics go beyond simple percentage agreement by accounting for the possibility of random agreement, giving us a more accurate assessment of consistency. For example, if 3 annotators are labeling speaker turns or emotional tones and all consistently tag the same segments with the same labels, a high IAA score confirms that the data is reliable. From a model perspective, IAA is critical because inconsistent data leads to noisy training signals. If annotators disagree frequently, the model gets confused by conflicting examples and predictions become less stable. Additionally, one could compare annotations to a ground truth dataset. Ground truth refers to a gold standard set of annotations that have been validated by experts or agreed upon through consensus. These serve as a benchmark against which all other annotations can be evaluated. In practice, a subset of audio data is selected and meticulously annotated by senior linguistics or domain experts. New annotations are then compared to its trusted source to calculate metrics such as accuracy, precision, recall, and F1 score. For example, in a speech-to-text task, we might compare how closely a transcription matches the ground truth, word for word. In a sound event detection task, we'd assess whether the correct sound type was tagged at the correct time. Ground truth comparison is particularly helpful for identifying systematic errors or inconsistencies in the annotation process. It gives us concrete evidence of whether the labels are correct and whether annotators are adhering to standards. And lastly, visual and auditory review combines human judgment with visual tools to review annotated data directly. Annotators or reviewers examine visual representations of the audio alongside listening to the audio itself. This dual approach allows reviewers to assess not only whether labels are present, but also how accurate and well-timed they are. For example, in emotion recognition, auditory review can help confirm subtle vocal cues that indicate emotional shifts. This method is especially useful when automated metrics like IAA don't tell the full story, such as when multiple valid interpretations exist, specifically when dealing with emotions. Visual and auditory review is also invaluable for quality assurance. Reviewers can catch edge cases, refine label categories, or even flag ambiguous segments. While this process can be time-consuming, it brings a qualitative depth that purely statistical evaluations may miss. Audio annotation is certainly a powerful tool, but it comes with several real-world challenges that affect the data quality, consistency, and ethics. First, there's the issue of data quality and volume. Real-world audio is messy, filled with background noise, overlapping speech, and varied recording qualities. Add to that the wide range of accents, dialects, and speaking styles, and it becomes clear why accurate annotation is very difficult. Second, expertise and consistency requires domain-specific knowledge, sometimes even in a medical or legal context. Even for general speech, understanding local slang or non-standard speech patterns can be tricky. Different annotators may interpret the same audio differently, leading to inconsistency. And finally, ethical concerns must be addressed. Audio data often contains personal or sensitive information. It's crucial to obtain informed consent to ensure strong data protection measures are in place to prevent misuse or unauthorized access. As my last topic, I want to get into how Annote has begun work on integrating some of these methods into everyday use. When running code locally, I chose to run it in VS Code. To start, we must import core libraries like Faster Whisperer, which is an open source speech-to-text model. We also must set up utilities for working with audio files, models, and storage. When setting up output folders, we make one to store the audio files and another for storing labels or metadata that is generated. Then it is important to check whether GPU is available and select the appropriate compute type. Large v3 is a version of Whisper that is accurate and compatible for optimizing speed and efficiency. This function takes a .wav file, a standard audio file format primarily used for storing uncompressed audio data, and passes it into the Whisper model. As a result, the model returns a full transcription of the audio, segment-level timestamps and text, and the detected language of the speaker. This pipeline only has the following functions. Later, as the pipeline is tested and can become more nuanced, we can look into integrating motion detection using OpenSmile and even sound event detection using a pre-trained model. So given in the example file harvard.wav, this function loops over the input and runs analysis. The result is a full transcription, segments like time started and time ended in language. So this is the sample audio that I chose to input into the pipeline. When running this code, the output produces the full transcription, timestamps, and the spoken language. A generalized method of this code can be found on Anote's synthetic data repo. But moving forward, to make this model more complex, I would choose to include some more timestamps, like if you wanted to identify keywords or phrases. For instance, if you wanted to pick apart the specific foods that it mentions in this audio and the timestamps, that would be a good thing to go under segments as well. Similarly, adding detections like the ones mentioned above, like emotion detection and sound event detection, would ideally be integrated later on into this pipeline as well. Thank you for listening.